Hello everyone. Today I will be presenting our paper Centered Symmetric Quantization for Hardware Efficient Low-Bit Neural Networks. Quantization is a method that can reduce the computational and memory complexity of neural networks. For precision, weights and activation require 32-bit floating point representation, but quantization can reduce up to 2-bit integer, of course with some performance degradation, but it provides significant memory and computational reduction. Now let's talk about linear and non-linear quantization. Linear quantization has uniform step size between adjacent quantization levels. Non-linear quantization has non-uniform step size between the adjacent quantization levels. Because of this non-linearity, non-linear quantization can better represent the underlying distribution. However, it requires special hardware design and cannot actually be realized efficiently on conventional hardware. Because of this, our work focuses on linear quantizer, which can actually be efficiently realized on conventional hardware. Let's look at the conventional linear quantizer. From here on, we will abbreviate conventional linear quantizer as CLQ. CLQ can be signed or unsigned. Unsigned CLQ is used for the activations. For example, the output of ReLU activation is unsigned, and signed CLQ is used for the weights. And here L and U are the minimum and maximum quantization levels. And one important thing to note here is that the minimum and the maximum quantization level for the signed CLQ are not same. This is because signed CLQ uses 2's complement representation, which does not have the same number of positive and negative values. Okay, so let's move towards the problems addressed in our work. The first problem is CLQ results in unequal number of positive and negative quantization levels. And we've already talked that's because signed CLQ uses 2's complement binary representation, which has unequal number of positive and negative values. However, the weight distribution usually follows approximately a zero mean Gaussian distribution, and because of that, CLQ results in significant quantization error. Now consider a quantizer which has perfectly zero-centered quantization levels. In our work, we call such a quantizer as centered symmetric quantization. So from now on, I'll abbreviate centered symmetric quantization as CSQ. So the question is CSQ really better than CLQ? And if so, then how much and why? The second problem is that CSQ realization on hardware using standard multipliers requires n plus 1 bit multipliers to realize n bit CSQ values, which is a very large overhead. To summarize, even though some works have used CSQ instead of CLQ, there's no study that explicitly compares CLQ and CSQ, and the inefficiency of the hardware realization of CSQ is ignored by all the previous works. In this work, we make three contributions. First, we formally define CSQ. Second, we systematically compare CLQ and CSQ. Third, we propose two efficient methods to realize CSQ. We define CSQ as a quantizer that has two fundamental properties. The first is that it must have uniform step size between quantization levels, which means that it must be a linear quantizer. The second is that it must have perfectly symmetric quantization levels, which means that the number of positive and negative quantization levels must be same. Here we analyze CSQ and CLQ. We quantize 4 precision ResNet 18 weights trained on ImageNet using CSQ and CLQ. So the x-axis represents the layers of ResNet 18, and the y-axis represents the percentage error reduction using CSQ. The red bar indicate that the error, the quantization error is reduced using CSQ, and the green bar represents that the quantization error reduces by using CLQ. So we can see that for 2-bit precision, we can reduce the quantization error by up to 30%, and for most of the layers, CSQ significantly reduces the quantization error. And as we increase the precision, the quantization error reduction becomes smaller. Now let's talk about affine quantizer. Affine quantizer is very similar to CLQ, except for it has an additional parameter, which is 0 point. 0 point can be used to shift the quantized distribution towards the positive or negative side. For example, consider p-ReLU activation output, which has a more diverse positive range and a suppressed negative range. So it may be better to have more quantization levels towards the positive domain and fewer quantization levels towards the negative domain. In such distribution, 0 point can actually shift the quantized distribution towards the positive side, and affine quantizer can better represent these type of distributions. However, affine quantizer actually results in some overhead to support the 0 point computations. And secondly, the 0 point is constrained to be an integer value, which restricts the expressiveness of affine quantizer compared to using floating point 0 point. Here we compare CLQ and CSQ using relaxed affine quantizer, which is a variant of affine quantizer where 0 point can take any floating point value instead of integer for the sake of analysis. The figure represents the 0 point distribution across layers for the affine quantizer used to quantize the weights for ResNet 20 and CIFAR 10, and the black line represents the 0 point for CSQ, and red line represents the 0 point for CLQ. We can see that the 0 point distribution is very close to CSQ for 2-bit precision, and as the precision increases, the 0 point distribution moves away from CSQ toward CLQ. Here we present our ImageNet experiment for comparing CSQ and CLQ, and we find out that CSQ is consistently better than CLQ. We see that just using CSQ for weights can give up to 0.5% improvement. We also see that as we increase the precision, the accuracy improvement using CSQ becomes smaller. So I hope we have convinced that CSQ performs better than CLQ at 2-bit and 3-bit precision, and as we increase the precision, the difference between CSQ and CLQ becomes smaller. You can see more analysis and results in our paper. Now let's talk about the hardware realization of CSQ. We propose 2 methods to efficiently realize CSQ on hardware. The first method is based on affine quantization, and this method is used to realize CSQ on standard multipliers, and this method results in a very small overhead. And the second method is based on bitwise binary neural network hardware, and this method results in no overhead. Let's look at the CSQ hardware realization using affine quantization. We analyze this 0 point for CSQ and CLQ, and we find that the difference between the 0 point for CSQ and CLQ is 0.5, which means that we can implement CSQ using affine quantization if we fix the 0 point to 0.5. However, this is not inefficient because 0.5 can actually be implemented using a bit shift operation. This method has very small overhead compared to using n+1 bit multiplier, and also the overhead is negligible for in terms of number of operations compared to the convolution operation. So the overhead is negligible for CPUs and GPUs, and the method can be used for any hardware using standard multipliers. However, it still results in some overhead for custom hardware such as FPGAs. Okay, now let's look at the CSQ realization on BNN hardware. We introduce a new binary encoding method for CSQ quantization levels. A 2-bit example for CSQ binary encoding is shown in the table. And using this binary encoding, we can use uh, so to compute the CSQ and unsigned CLQ multiplication, we can use AND pop count. This method results in almost no overhead, and because of the bit processing nature of the BNN hardware, we don't need to change the hardware to increase or decrease the precision. The disadvantage, however, is of course that this method cannot be applied to standard multipliers. Finally, let's look at the FPGA experiments. We see that CSQ with affine hardware can significantly reduce the area and latency compared to the relaxed affine quantizer. And also we see that CSQ has almost no overhead on BNN hardware compared to CLQ. Okay, to conclude, we have shown that CSQ for weight quantization can actually provide a significant performance advantage compared to CLQ at 2-bit and 3-bit precision. However, going beyond 3-bit precision, the performance improvement starts to become very small. Secondly, we propose two methods for efficient realization of CSQ on hardware. The first method is for standard multipliers using affine quantization. This allows CSQ realization with a very small overhead. And the second is for BNN hardware, which allows CSQ realization with almost no overhead. Thank you very much for listening to our presentation, and please feel free to contact us if you have any questions.